Hi everyone and welcome on board your really long-haul flight. On this channel we've put together a compilation of some of the most jaw-dropping moments from the sky, so now all that you need to do is find a comfortable place to sit, bring out your favorite drink, sit back and relax. We have so far seen that the Comet was the first real jetliner and that the Boeing 707 was a jet who really defined the shape of several generations of jetliners that came after it. But before all of that, there was a humble piston engine aircraft that managed to persevere for decades, even after the arrival of the jet age. And for at least one generation, this was the aircraft that gave people their first taste of flying, either in peace or during wartime. There are several of these almost magical aircraft still flying around today, and if they stick around for another decade or so, it would mean that this type have been flying for 100 years. We are of course talking about the story of the iconic and wonderful Douglas DC-3 and how this beloved aircraft almost didn't even leave the drawing board. Stay tuned. Before we get going properly, I have a little quiz for you. Here's a picture of the cockpit of a DC-3, and up here over the windshield we can see the magneto switches for the two engines. You know, the switches that will allow the engines to actually start when they're turned around. But all of the other engine controls are located in a different part of the cockpit between the two pilots where you might expect to find them, so why would Douglas place the magneto switches up there? Have a think about it and we'll get back to it later on. The DC-3 is an all-metal aircraft, but to understand how it got off the drawing board and into service, we have to start by talking a little bit about wood. On the 31st of March 1931, a Fokker F-10 tri-motor airliner crashed in Kansas, killing all 8 passengers and crew on board. The operator of the aircraft was Transcontinental and Western Air, maybe better known as TWA. This was a high-profile crash because one of the passengers was Knute Rockne, a famous college football coach. An investigation showed that the crash was likely caused by the structural failure of one of the wing spars. A wing spar is basically a beam stretching span-wise from the fuselage to the wingtip, holding together the rest of the wing structure and connecting it to the fuselage. As you probably guessed, in the Fokker F-10, the main wing spars were made of wood, in this case of a kind of wood laminate. The most likely cause of the failure was that excess moisture had seeped into the wing, gradually loosening the bond between the layers of wood, eventually causing the failure. Now, the use of wood for aircraft structures was quite common at the time and would remain in use for some small general aviation and experimental aircraft to this day. It's actually a great, resilient and flexible material. But after that 1931 crash, the FAA introduced new rules severely restricting wood as a structural material for commercial passenger planes. And because of the high-profile nature of the TWA crash, the matter got plenty of public negative attention, which meant that the airlines now suddenly wanted to replace their older planes fast. This resulted in an aircraft design and manufacturing rush, and immediately TWA had a serious problem. They couldn't find someone to make the planes that they needed. The first company that TWA turned to was, of course, Boeing, who even before that infamous crash had a flying prototype of a very promising new aircraft called the Boeing 247. This was an all-metal airliner with seats for 10 passengers. Now, that passenger capacity was a bit below that of the Fokker F-10, but apart from that, the aircraft would fit TWA's needs for a new airliner perfectly. But there was one small problem with the Boeing 247. Basically, Boeing wasn't just Boeing, the aircraft manufacturer at the time. Boeing's own history is a very long story by itself, but the point here is that by 1931, when the TWA accident happened, Boeing was part of a company group called the United Aircraft and Transport Corporation. And this group also included what we now know as United Airlines. So when TWA came knocking on Boeing's door looking to buy its 247 all-metal airliner, Boeing responded that its production of the type would prioritize, well, United of course. If TWA wanted the 247, they would have to wait until Boeing first finished making 60 of these aircraft for United. But instead of waiting, TWA decided to invite offers from multiple other manufacturers for an aircraft variant that would meet its design needs. This, an airline asking manufacturers for its own aircraft design, actually wasn't unheard of in the 1920s and 30s. Obviously, this aircraft would need to have an all-metal structure, but TWA also wanted it to be able to carry at least 12 passengers and have 3 engines like the Fokker F-10 did. They also had some other requirements involving, for example, the speed and range it would need to be able to perform. TWA wanted 3 engines because they wanted to reverse the public's negative safety perception after the accident I mentioned before, and to achieve that they wanted an aircraft that would be able to take off and land even after an engine failure, and they didn't think that this would be possible with a twin-engine aircraft of this size. Now, Donald Douglas from the Douglas Aircraft Company saw the tender that TWA put out and became interested. But up until that point, they had been focusing mainly on making planes for the US military. This meant that they had no real experience in making passenger airliners at all. Douglas, however, believed that he could build an aircraft with 2 engines that would meet TWA's size and performance specifications, but initially he had some doubts whether or not it actually existed a market big enough for the company to be able to make a profit after their development costs. As it would later turn out, Douglas would not need to worry about that, although in a weird way, the incredible success of his aircraft would later become a huge problem, not only for his competitors, but also for his own company. The first aircraft that Don Douglas made for TWA was called the DC-1. By the way, the letters DC mean Douglas Commercial, and obviously the DC-1 was the company's first aircraft in that category. Its similarity with the later DC-3 is immediately obvious if you look at it, and more importantly, TWA absolutely loved it. TWA eventually put this first aircraft into service, only with a few modifications, but they requested a few more changes to the definitive production version. That version was aptly named the DC-2, which had the same wing as the DC-1, but a slightly longer fuselage to better accommodate 14 instead of 12 seats, and it also had a more powerful version of the Wright Cyclone R1820 radial engine. Now, Don Douglas wanted to build at least 100 of these planes to make the project profitable, and TWA initially bought only 20 DC-2s, plus the initial DC-1. But Douglas finally ended up making nearly 200 DC-2s for various customers from the year 1934 until 1939, making the project a relatively big success. Now, even before the production ended, Douglas had been working on a couple of newer designs based on the DC-2. One of them was the B-18 Bolo, which was a military bomber with a slightly bigger wing and a different fuselage, but otherwise using much of the same systems as the DC-2. This bomber is almost forgotten today, but Douglas actually made 350 of them starting in 1936, and in that same year, before finishing production of the DC-2, Douglas introduced the DC-3. And it would soon become obvious that its timing couldn't have been better. Now, you might assume that the DC-3 is just an updated, enlarged version of the DC-2, and this would be, well, mostly true, but there is a bit more to it than that. You see, initially, the aircraft that we all refer to as the DC-3 was not actually called this at all. It was known as the DST, which stood for the Douglas Sleeper Transport. The original DC-2's cabin had been 1.7 meters or 66 inches wide, which was good enough for an aisle with 1 seat on either side of it. This is what we normally refer to as a 1-to-1 layout. Now, the DC-3, or the DST, had a 2.3 meter wide cabin, which would fit 2-to-1 or even a 2-to-2 seat layout, which also later became standard. But to begin with, the reason why the new aircraft was this wide was because someone, specifically American Airlines CEO Cyrus Rowlett Smith, wanted to install sleeping berth in the aircraft. And the idea was to place these berths above the seats instead of overhead luggage racks, because overhead bins weren't really a thing back then. If you look at the picture of an original Douglas DST, you will notice that above every second passenger window there's actually a smaller window, and this was for the passenger who was lying in the berth. Now, I'm not sure how useful a window was when people wanted to sleep, but if they wanted one, there it was. American Airlines bought 20 DSTs configured aircraft, and a few other airlines also got them. These planes had basically the same seat capacity as the older DC-2s, 14 or sometimes 16 seat, but this didn't last very long. Turns out that most customers would instead order their aircraft in the form of a DC-3 with no upper berth windows and anywhere from 21 to 30 seats instead, making it much more profitable. Before Douglas switched its production to military orders back in 1942, they made just over 600 DC-3s and DC-3 Alphas, where the 3 Alphas had more powerful Pratt & Whitney R1830 twin Wasp engines. And if the aircraft's production had ended there, at 600 aircraft, it would probably have been seen as a considerably big success by all measures. But that's not what happened. Douglas would instead end up making well over 10,000 military C-47 Skytrains, or Dakotas as they were known by the British. Military versions had other designations, including C-48, C-53 and more, depending on whether they were meant for troops, VIPs or cargo. 600 commercial and 10,000 military aircraft is an amazing production run. And remember, there are also those 350 older bombers that were based on the DC-2. But these are just the numbers of aircraft that were made directly by Douglas. There were also factories in a couple of other places who were making versions of the DC-3 under license. The most prolific of these was Lisunov in the Soviet Union, who made over 6,000 Li-2 units. The last of these left the factory in 1952, making them the newest DC-3 factory variant of all, but of course that's not including the DC-3 modifications, but we will get to those later. Instead, perhaps the most surprising producer of a variant of the DC-3 under license was Japan. Nearly 500 aircraft were made in total between two manufacturers, Showa and Nakajima. The first of these were basically very close to the originals with American-built Pratt & Whitney radial engines, but later the Japanese companies would modify the aircraft in order to ease production and also switch to Japanese engines. Now, listing the different roles of the C-47 and other military variants of the DC-3 would basically make a 1 hour long video by itself. The planes were basically used for everything, from carrying troops and cargo to photo reconnaissance, dropping parachutists and even dropping bombs in some places. And interestingly, the end of the Second World War did not spell the end of the military usage for the C-47s and other variants of the DC-3. The aircraft also played a key role in the Berlin airlift in 1948 and 49 and was even used as a gunship during the Vietnam War. The C-47 maybe wasn't the biggest or the best all-around transport aircraft. Plenty of other bigger planes emerged during the war, like the C-54 Skymaster, which was a military Douglas DC-4 for example, but the smaller twin-engine C-47 was ubiquitous and could get in and out of tighter fields, making it completely indispensable during the Second World War. However, the type then became equally indispensable in many parts of the world long after the war had ended in the design it was originally thought to be used in, commercial aircraft. And that was because thousands of the military aircraft that had survived the war later converted to DC-3 passenger aircraft. Now, a funny side note here is that some of the earlier military planes had originally been built as DC-3s and then been converted to military use before finally being reconverted back to commercial use again. Other World War II aircraft were also converted to commercial or other civilian roles after the war, but nothing at the same scale as the C-47. A sea of converted DC-3s became a boon for small airline startups after the war, both in the United States and in other parts of the world. It's worth pointing out here that before the war, flying by air was really quite rare, something that very few people could afford to do. But the war didn't just generate all of these airplanes, it also led to the creation of hundreds of new airports, creating opportunities for more passengers, new airlines and many former military pilots to fly. But this also created a very strange problem, particularly for aircraft manufacturers. You see, with the jet age just around the corner and loads of new technologies emerging, the manufacturers had started approaching the airlines with new ideas for better, faster and more capable airliners in order to replace the DC-3. But for the most part, nobody really listened to them. By the end of the war, the DC-3 was obviously very slow and not particularly comfortable or modern. It didn't have a pressurized cabin, so it had to fly through or preferably around bad weather. But buying a brand new aircraft was much more expensive, often many times more expensive than buying a whole fleet of older, slower, but still dependable DC-3s. For manufacturers, the only way to sell anything new became instead to make it much bigger, preferably with a longer range, putting it in a completely different market than the DC-3. Interestingly, in the United States, the FAA soon started to become quite worried about the ways that some ex-military aircraft of multiple types were being used commercially after the war. The agency actually started tightening its rules in order to try and prevent the widespread use of these planes, and that gave Douglas an idea. The company would offer what it called the Super DC-3 or the DC-3S, which in practice was an extensively modified version of its original aircraft. The outer wing sections would be replaced with longer ones that had flush rivets and a swept trailing edge, plus the fuselage would be extended and the aircraft fitted with more powerful engines. These engines also necessitated a bigger and more square vertical stabilizer, which is the most recognizable feature of the Super DC-3. These and other modifications helped increase the cruise speed of the aircraft from around 180 to 220 knots, which was a significant but not a huge difference. Douglas offered this as an upgrade to the airlines, especially those who already had DC-3s in their fleets, and the idea was that this upgrade would also satisfy the newer FAA safety regulations, which Douglas thought would be a great selling point. So, how many Super DC-3 modifications did Douglas sell? The answer is none, at least not to the airlines. Because as it turned out, modifying the standard old DC-3s to meet the FAA's newer and more stringent safety regulations was actually possible and much cheaper than buying or upgrading to a Super DC-3. It's quite ironic that given that the FAA's rules for commercial aircraft motivated the creation of the Super DC-3, the only buyer of this airplane ended up being the US Navy. About 100 of these planes, designated the R3D8s and the later C117Ds, would enter service with the US Navy and the Marines, and the last one of them didn't leave service until in the 1990s, with some examples still flying today in the hands of commercial operators. There were many more modifications to the DC-3s for specialized roles in the years that followed. A lot of different companies modified them with turboprop engines, including Basler, who is still rebuilding and modifying these aircraft today. Many people have fond memories of these old birds today, and I completely understand why. They're beautiful. A couple of years ago, I actually made a video where I was exploring the outside and the interior of a DC-3 that was once operated by Scandinavian Air Systems. Just like we do, you'll be amazed how similar this aircraft actually is to modern airliners. It tells a little bit about how slowly things moves in the aviation industry. It was incredible to see how similar the equipment and the placement of gauges, switches and controls are to commercial aircraft used today. But of course, if you think about it, the 737 that I fly was heavily based on the 707, whose prototype first flew in the mid-1950s. That's only 20 years or so after the DC-3's first flight, so there is a good reason why many of our cockpits today have so much in common with this lovely old bird. And this finally brings us back to those magneto switches above the windshield. Have you figured out why they are there yet? Well, for the explanation of this, we have to give a shout out to Mikey McBrien and his father, Buffalo Joe of Buffalo Airways. The magneto switches are there so that they are visible from the outside of the aircraft when the pilots do their walk-around before departure. Among many other things, the DC-3's walk-around involves checking that the propellers can move freely, but before you even put a hand on the propeller, you need to check that the magneto switches are switched off, so that the engine doesn't start when you turn it. The only way to see that from the position you are standing is if the switches are on the overhead panel, and part of me is actually wondering if the fact that the start switches on the 737 are also placed there is a distant shout out to this old bird. I find it amazing to think that some of these planes are still in active commercial service today. Often the reason for this are economic. The planes are so overbuilt that they're still going happily, of course, provided that they're properly maintained, and they're still cheaper to purchase and operate than many alternatives. But likely the biggest reason that they're still around is because they can still fulfill a role that very few other aircraft can. It is one of the best looking, if not the best looking airliner ever made, but there are people who saw it in a very different light, and instead of ushering in the era of supersonic passenger travel, this delta wing beauty slowly faded away without a successor. So, was Concorde a lost opportunity for commercial aviation or just a truly wonderful failure? Stay tuned. By now, I have already made several videos where I have looked at some of the most iconic airliners of the previous century and how they shaped the aviation industry that surrounded them. In quite a few of those videos, I've highlighted how rapid the pace of development of aviation was back in the immediate post-war era from the late 1940s to the 60s. I have to keep returning to this because understanding the context behind these planes is almost impossible today otherwise. Nowadays, a new airliner can take over a decade to go from project launch, when the first orders are announced, to the day when they actually carry paying passengers. But back then, things just worked completely differently. To show you what I mean by that, I'll start by giving you a quick comparison. In one of my latest episodes that I did here on the channel, I explained that the Boeing 777X is now estimated to take 12 years to enter service, and it's not even an all-new aircraft design. And with that in mind, remember that the first Boeing 707, the most successful early jetliner ever, had its inaugural flight in December 1957, and the first Concorde flew in March 1969. This means that the Concorde flew just 12 years after the first widely successful jetliner, the 707, or 20 years after the passenger jet era begun, which is insane. I mean, I have been a commercial pilot for longer than that. Okay, technically I'm cheating a little bit here, because the timeline would have been longer if I was comparing the service entry dates of these jets to each other, but whichever way you look at it, the Concorde was definitely way ahead of its time and appeared super early in the jet age. Now, the Concorde had to be ahead of its time because all new aircraft that were developed back then had to be really bold designs if they were going to have any hope of actually succeeding. The 1950s and 60s was an era when some aircraft could become obsolete just weeks or months after entering service due to the introduction of newer, better engines, new discoveries in aerodynamics, and even new alloys and other materials. With such a rapid pace in development, and with military jets flying at supersonic speeds already in the 1940s, everyone in the industry knew that obviously it was just a matter of time before the first supersonic airliner would also come. People also believed that once that happened, once they actually started flying, well then practically all new airliner designs would then follow, and they would also be supersonic, maybe apart from some freighters and smaller regional aircraft. This means that even when we go back to the 1950s, before even the Boeing 707 flew, everyone in the industry was keenly aware that a supersonic airliner development race was somewhere over the horizon, and they all wanted to be ready for it when it came. That's the reason why a British research facility called the Royal Aircraft Establishment started conducting feasibility studies on supersonic passenger aircraft all the way back then. And the main obstacle that they needed to overcome was the construction and shape of the wing. A supersonic airliner obviously needed a wing that would be as efficient as possible at its super high cruise speeds, but the aircraft also needed to be able to take off and land at comparatively low speeds. So this meant that its wing had to operate well in those conditions as well. And at that time, that seemed like almost mutually exclusive. You see, conventional aircraft use extending flaps and slats to effectively enlarge and reshape the wing so that they can generate high amounts of lift during the takeoff and landing phases. After takeoff, these high lift devices then retract and get tucked away during the cruise to give favorable drag characteristics at higher speeds. But pulling off that same trick in a supersonic aircraft turned out to be much more difficult. The aerodynamicists at the time knew that a very narrow trapezoidal wing would work well at higher speeds, and there were already small fighters like the Lockheed F-104 who used that design. But enlarging such a wing to make it suitable for an airliner would generate way too little lift at lower speeds during takeoff and landing. And on top of that, it would also be too thin for housing the flap and slat mechanisms, or even for storing fuel. The birth of the Concorde basically only became possible when a pair of aerodynamicists, Johanna Weber and Dietrich Küchemann, started working on an idea which would eventually be known as the slender delta wing concept. Johanna and Dietrich knew that wings with a swept leading edge performed really well at transonic and supersonic speeds. Delta wing concepts already existed at this point, but were believed to generate relatively little lift at low speeds. But what Weber and Küchemann showed was that a specially designed delta wing, which extended far enough forward and rear along the fuselage, could, under the right conditions, generate vortices along its leading edges, who helped to generate a lot of lift, especially at lower speeds. Now, normally, aerospace engineers try to limit wingtip vortices from the wings in an effort to reduce drag, but in this case, these vortices became vital in generating this necessary extra lift and enabling the Concorde to operate from existing runways. And to make things even better, this also meant that the wings would work even without complicated flaps or slat mechanisms. The only caveat though with this design was that the aircraft would have to take off and land at very high angles of attack, which then introduced other challenges like the need for a drooping nose to give the pilots the chance to actually see something during those phases of flight. But those problems were easier to solve. This aerodynamic research, however, was extremely key in the development of the aircraft. Anyway, once those problems were solved, there were even more work needed to ensure that the design's center of lift would be at a desirable position. Now, this is a little bit complicated to explain properly here, but in general, the lifting force that is generated by the wings can change position at different speeds and angles of attack. Now, if you're balancing a model aircraft on your finger, the point which holds the aircraft can be seen as the center of lift, and on a still object, this point must then coincide with the center of gravity to avoid an aircraft pitching over on your finger. But for an aircraft in motion, those 2 points must differ from each other for the aircraft to remain stable, and we use aerodynamical forces to then balance the aircraft out. With conventional wings, this is pretty easy to do with the help of a horizontal stabilizer in the back, but that wasn't so easy with these delta wings. Now, in the end, the design teams chose what's called an OG platform, or an ogival wing, which ended up satisfying all of their requirements. So, this research made the concept of a supersonic airliner theoretically possible, but there was still quite a lot of work in actually developing it, building it, and making it work for actual transatlantic passenger flights. Now, in order to analyze in detail every technological development which made the Concorde possible, I would need to make several of these videos, which I actually might end up doing. But instead of doing that right now, I will concentrate on some of the more unique aspects of this aircraft design. In terms of size, the Concorde was about 61.5 meters or 202 feet long, which is similar to the length of a Boeing 787-9. But whilst the 787-9 usually seats around 300 passengers or so, the much narrower cabin of the Concorde meant that it could only fit around 100 or so. Its wingspan was 25.6 meters or 84 feet, which is actually less than even an Embraer E175, let alone a 787, and that was obviously because of the Concorde's unique delta wing. I've explained the purpose behind the wing design already, so let's instead talk a little bit more about what else was needed to make the Concorde fly efficiently. The varying flight and handling characteristics of the plane at different speeds led its designers to incorporate a fly-by-wire system to control it. Now, it was an analog design with some mechanical backups for different flight controls, but it was still the first of its kind, at least in an airliner. On top of that, the Concorde also needed forward and rear trim tanks, meaning tanks that fuel could be pumped into or out of in order to change its center of gravity. This was because even with its sophisticated ogive wing, the Concorde's center of lift would always change as it reached its supersonic cruising speeds. The position of the center of lift could then vary as much as 2 meters moving towards the rear above a certain speed. Now, If the weight configuration of the aircraft remained the same, this would then cause the nose to want to drop or for the aircraft to pitch down. Like I mentioned earlier, we normally adjust the pitch variation of an aircraft by using the elevator trim, which in most airliners just moves the horizontal stabilizer, and this actually generates a small amount of drag, which is acceptable at the speeds that we typically fly. But at supersonic speeds, these pitch variations would be much greater, and the Concorde doesn't even have a separate horizontal stabilizer, so that's why using trim tanks was so important. Moving the weight back and forth has the same result, but with no aerodynamic penalty, and actually some large conventional airliners like the MD-11 and some versions of the 747 also have trim tanks for the same reason, mostly to be more economical, not to actually control the aircraft though. Now, here it's also worth mentioning that as advanced as the Concorde's wing was, the construction of its fuselage was relatively conventional. By the time the Concorde's design was being finalized, aerodynamicists were already quite familiar with a principle called the area rule. In simple terms, this principle says that aircraft flying at transonic or supersonic speeds need to have their shape formed in such a way that if we were to slice them perpendicularly, the cross-section of each slice would change as smoothly from one slice to the next as possible, without any sudden bends or changes. The purpose of this is to reduce wave drag caused by supersonic shock waves, and the way to achieve this varies depending on how fast that we need to go. In practice though, following this rule means having to vary the cross-section of the fuselage, making it narrower where it meets the wing. And that's difficult to do in an aircraft with a pressurized passenger cabin made out of aluminium. That's why the engineers working on the Concorde early decided to ignore this principle and stick with the standard tubular fuselage. But even though they took this simpler way, they still had pretty significant challenges in designing it because of the extreme temperatures that the plane was going to be subjected to during each flight. The Concorde would famously get 30 centimeters or 12 inches longer in cruise because of thermal expansion, and this meant that the engineers had to choose their building materials carefully to ensure that it wouldn't develop fatigue problems over time as it expanded and contracted. This was also what ultimately limited the Concorde's maximum cruise speed. You see, normal airliners have a maximum speed which depends on structural and aerodynamic considerations, meaning that we basically limit our speed to a safe point well below a speed where aerodynamic forces could overstress the aircraft. But in the case of the Concorde, its top speed was often quoted as Mach 2.04, but it was actually temperature limited rather than aerodynamically limited. The crews were monitoring a temperature sensor at the nose to make sure that it didn't go higher than 127 degrees Celsius or 260 degrees Fahrenheit, and this in turn meant that on colder days they could actually fly the plane a bit faster. Now, another area where the Concorde was, well, I would say a bit old-fashioned was with its engines. In terms of their origin, the Rolls-Royce Olympus engines of the Concorde were a relatively established design, which was first used in the Avro Vulcan bomber already back in the early 1950s. But that's a little bit misleading, because there was plenty of developments made to that engine between the Vulcan and the Concorde. Rolls-Royce spent quite some time developing an updated supersonic version of this engine for use with an aircraft called the BAC TSR-2, a bomber intended for the RAF. That aircraft would eventually be cancelled, but that didn't stop Rolls-Royce from continuing to develop its engines. They later partnered up with Snecma, a French engine maker called Safran today, and together they developed the final Concorde version. Now, most modern airliners today use turbofans, which is an evolution of the earlier turbojets. The difference between a turbojet and a turbofan is that in a turbofan, most of the air coming into the engine then goes through the fan and bypasses the engine core itself, which can increase the engine's efficiency substantially. But that assumes that the aircraft this engine is mounted on is flying at subsonic speeds. At supersonic speeds, we have a couple of issues who makes the use of high bypass turbofans a bit problematic. Firstly, as we see with every new generation of aircraft today, high bypass turbofans are getting bigger and bigger frontal areas. And this larger face of the engine increases its drag at higher speeds, and secondly, this area can make it really difficult to ensure that no supersonic airflow makes it into the engine, where this supersonic airflow wouldn't work well at all with its fans or compressor stages. So that obviously begs the question, if we have an aircraft that can fly at Mach 2 or twice the speed of sound, how can we keep the airflow from going into any of the engine components at supersonic speeds? Not just the turbofans, any type of engine. Well, this is where we have to talk about the Concorde's engine air inlets. You see, if you imagine a river with a steady amount of water flowing through it. Now, imagine that you need to slow down the flow of water in this river at a specific point. How would you do that? Well, one way would be to suddenly widen the river at that point, right? And this is kind of what the engineers and aerodynamicists did using the engine inlets for supersonic jets. They designed the inlets so that they could limit the amount of air going in, with the air then expanding inside of the inlet to slow it down before it hit the engine fan. Now, in reality, this process is actually much more complicated than that, because unlike water flowing in a river, the air can be compressed to accomplish the same slowing effect. But the point here is that aircraft like the Concorde needed inlets whose configuration could vary depending on their speed. This wasn't just a matter of efficiency, by the way, it was also a safety issue. The Concorde was equipped with 4 engines in 2 pairs situated under each wing, with each engine having its own variable inlet. This meant that if one engine failed as the aircraft flew at Mach 2 at 55,000 feet, the inlet would need to be reconfigured immediately to reduce the drag on that dead engine. For this reason, the Concorde didn't just have engine inlets with a vario geometry. It also had an inlet-by-wire as well as a throttle-by-wire engine control system, which are the precursors to modern full-authority digital engine control or FADEC systems. The throttle-by-wire system also controlled the nozzle at the back of the engines in order to deliver maximum thrust at every speed and altitude. All of these systems meant that the Concorde's engines were actually incredibly efficient, even though they were a relatively old design. The only caveat being that they were only incredibly efficient in cruise. At subsonic speeds, and even when they were taxiing, the Concorde's engines instead burned quite a bit more fuel than any of the other designs did. Some said that a Concorde would burn as much fuel to get from its gate at London Heathrow to the runway as an Airbus A320 would burn during its whole flight from London to Paris. Now, in the end, the Concorde actually ended up being the second supersonic airliner to have its first flight, after the TWA-144. But as I explained in my video about that one, the Tupolev actually entered service much later and was constantly beset with problems until it was ultimately withdrawn. But what about Boeing and the other American manufacturers, and why didn't the Concorde itself have any successors? Well, I gave you a bit of a clue about this in the beginning of the video when I was making those timeline comparisons with the Boeing 707. You see, the Concorde had its first flight in March 1969, but actually didn't enter service until 1976, as its engineers were constantly working on solving all of its infancy problems. And between 1969 and 1976, the aviation industry ended up changing completely. In 1971, Boeing's 2707, the supersonic challenger to Concorde, was cancelled before the prototype was even built. This happened after very long delays, which were partly due to some early design decisions. Instead of the Concorde's ogive delta wing, the American manufacturers who were competing for the US Supersonic Transport or SST program had their own ideas on how to solve it. Lockheed's design was eventually actually similar to the Concorde's, but much bigger, meaning that it would have required much longer runways to operate. North American's design, the NAC-60, looked a lot like the B-70 Valkyrie bomber, and it had a delta wing with leading-edge high-lift devices and forward canards. And Boeing's entry, the 2707, which was eventually selected as a winner, featured a much more ambitious, complicated and quite heavy swing wing design. Boeing eventually abandoned that idea in favor of a fixed delta wing with additional tail surfaces instead, together with a significantly reduced size and speed. All of these changes slowed down the 2707 program a lot, and it also increased its costs dramatically, which eventually contributed to its cancellation. All of this would end up being a massive blow to Boeing, who were already struggling at the time with a more general downturn in airliner demand. But in a strange way, this cancellation might well have been a blessing in disguise for them because of what was about to happen in the rest of the world. You see, supersonic speeds came with higher drag and obviously with that a much greater fuel burn, but the economics of the plane could still work if the price of fuel continued to stay really, really low. But in 1973, the Yom Kippur War caused a fuel crisis that would force the airlines to completely rethink the way that they were operating and instead start to favor really, really efficient large capacity aircraft instead. So even before its service entry in 1976, the Concorde was already on very shaky ground. And on top of that, complaints about airport noise from its operation also persisted before and especially after its entry into service, although in reality it actually wasn't that much noisier than some Boeing 707s that were also operating at the time. But the sonic booms which Concorde created as it went supersonic soon created legislation which banned it from transitioning into supersonic flight over land in a lot of different countries, significantly limiting its available routes. All of this meant that even though Concorde was unquestionably ahead of its time when it was created, by the late 1970s it had already fallen behind the times, economically and perhaps also socially. It was obviously raw awesomeness for avgeeks like myself, but a flop for accountants, so any thoughts of successors with maybe an area rule corrected fuselage or with newer engines vanished before it even went into service. And it's now 20 years since this majestic plane was grounded forever after its final revenue flight in October 2003. The Concorde never fully recovered its previous image after a terrible accident in July 2000, which I actually covered over on the Mentour Pilot channel. So, looking back, did the Concorde actually have much of a legacy? Well, actually it absolutely did. I already mentioned fly-by-wire, throttle-by-wire, and quite a lot of the systems and design details in the Concorde would later find themselves in Airbus cockpits as well. For example, it had blue, green and yellow hydraulic systems, just like on Airbus, and even the shape of its throttles looks quite similar to what we find in many Airbuses today. But there are much more meaningful connections between the Concorde and Airbus than those ones. Remember that design team responsible for the wing concept of the Concorde? Well, the same people, Johanna Weber and Dietrich Kuschemann, went on to lead the design of the wing for the Airbus A300B. The efficiency of that wing, along with the fact that the A300 only had 2 engines of course, made it 30% more efficient than competing planes like the Lockheed TriStar. And this secured its future, and with that also the future of Airbus. We're now seeing companies like Boom Supersonic who are hoping to eventually fly a supersonic airliner again, but given the industry's even greater focus on efficiency, they will definitely have their work cut out for them. We have covered many different uses of the Queen of the Sky in this series so far. Everything from a flying telescope to a space shuttle carrier, but in today's episode I will tell you about some of the strangest roles of all, one of them even a little bit scary. Stay tuned. Now before we start, I have a little quiz for you. Aircraft often sport a lot of small antennas protruding from their fuselage, but how long do you think the longest aircraft antenna in the world is, and what is it used for? Well, have a think about it, and I'll come back to that a bit later. Now, from the very beginning, Boeing was actually hoping that their majestic 747 that they had created would attract a lot of interest from more users than just airlines, and they were particularly hoping for the military. Remember, at the time the 747 was the world's first wide-body, and compared to almost any other aircraft out there, it was simply enormous. So Boeing had good reasons to believe that such a beast would come in handy for many other new military concepts. One of Boeing's earliest ideas involved something truly outrageous, which was, and I'm not kidding here, a flying aircraft carrier. Obviously, the aircraft carriers that we use today, the ones that travel on water, are used to enable military operations around the world, or even used as a show of force by the countries who have them. But these sea-going aircraft carriers and escort fleets have a natural limitation in how quickly they can deploy and where they can move. So, what would you do if you would need to send fighter jets to somewhere in the world in hours instead of days or weeks? Well, obviously, then you would need to use an aircraft carrier that could fly, right? This might sound ludicrous today, but the concept of an airborne aircraft carrier, or an AAC, is something that the US Air Force actually examined very seriously throughout the 1960s and into the early 1970s. And if you think about it, given the incredibly rapid developments around aviation back during the Cold War, this idea maybe wasn't as crazy as it sounds on the onset. And you need to also take into account that launching an aircraft from another wouldn't even have been that unique back at that time. Because the Bell X-1, which was the aircraft who first broke the sound barrier, was, for example, launched from a modified B-29 bomber, and a number of other test vehicles were also launched from B-29s, B-52s and other aircraft in the years that followed those first X-1 launches. But of course, in this case, a true aircraft carrier would have to be constructed not to just launch aircraft, but also to be able to recover them. Now, as it turns out, the US Air Force had already tried such recoveries before, but with some quite questionable results. The first idea they used was to design a tiny fighter who would be able to protect groups of bombers during long missions. One of those bombers in the group would then carry these small fighters, and a prototype was actually built named the McDonnell XF-85 Goblin. Launching this little aircraft from its mothership wasn't a huge problem, but recovering it with a type of trapeze mechanism obviously was a completely different matter. Some successful recoveries were actually made, but on several occasions the aircraft was severely damaged during their attempts to dock, and since the Goblin didn't have any real landing gear, it meant that the test pilots got to do a lot of practice in performing belly landings. More tests with different aircraft would eventually prove more successful, but by then it basically didn't matter anymore. Aerial refueling had at the time become mainstream, and that allowed regular fighters to escort bombers and go as far as necessary without having to be launched or retrieved along the way. And also, those little fighters that had been developed for the role weren't as maneuverable as other fighters, so their usefulness in defending bombers would have been, well, questionable. So, if they had already tried this and found it to be without merit, well, then why did the Air Force return to the idea of an airborne carrier when the 747 came along? Well, like I said before, it really was a matter of size. The fuselages of most bombers in the 1940s and 50s were relatively small and narrow. But the much greater volume inside the cabin of a 747 meant that it was suddenly physically possible to fit more, larger fighters inside of them. Because of this, following on from those earlier studies that were made back in the 1960s, in 1972 the Air Force commissioned Boeing to create a new study, specifically examining the feasibility and usability of an aircraft the size of a Lockheed C-5 Galaxy as an airborne aircraft carrier. But what Boeing instead did was they examined both the C-5 and the 747, together with a number of configurations of miniaturized fighter aircraft, or microfighters, in this study. It ultimately indicated that either variant could carry as many as 10 of these microfighters, and to do that, the ACCs would have to be fitted with 2 launch and recovery bays, plus an aerial refueling boom for fighters that didn't need a full recovery. The idea was then that the microfighters themselves would be designed by Boeing, and they could be quite small, but still be able to carry weapons for a variety of different missions and assignments. The carrier aircraft would obviously also carry personnel to rearm and refuel them, and of course the carrier would be able to take on fuel in flight to keep itself and its tiny little fleet in the air. Boeing's study ultimately concluded that the 747 was a more suitable candidate for the job, because a lot of the C-5's internal volume would be lost in the conversion into this new role, and Boeing also claimed that the 747 had more potential for an increase in gross weight than the C-5 had, and that the C-5 had some weight and balance issues. Boeing also pointed to the need to provide in-flight refueling and dual recovery of aircraft, which they claimed was easier to do with the 747, and also, finally, that the 747's airborne aircraft carrier would be both faster and have better range than the C-5 had. Now, Boeing had at the time just lost the competition of the large military cargo aircraft that eventually became the C-5 Galaxy to Lockheed. So maybe they were over-pushing the benefits of their own design just a little bit, but still. Obviously, a more detailed study would be needed for the Air Force to actually go ahead with this project, but as I'm sure that you've already guessed, they ultimately didn't. Again, aerial refueling and more efficient engines made the value of this concept very questionable. But some elements of the Boeing study did actually make it onto the 747s. At the same time that Boeing's engineers were writing that report on a possible airborne aircraft carrier, Boeing and the US Air Force had already modified the first ever 747 into an aerial refueling tanker, and they were conducting some rather interesting test flights with it. The Air Force wanted a refueling tanker that would be larger, faster and capable of delivering fuel at a higher altitude than the KC-135 could at the time. And the reason for that? Well, that was primarily to make refueling easier for the SR-71 spy planes, one of my favorite non-civilian aircraft of all time. The SR-71 flew in the fringes of the airspace of the Soviet Union, China and other countries of interest at the time. But for the most part, these aircraft would always start their missions inside of the continental United States. Well, okay, some of these jets were eventually based in the United Kingdom, and at times they would have technical issues, forcing them to diverse elsewhere, which would bring some rather interesting diplomatic results, but that's another video. Anyway, flying literally halfway around the world and back for some missions meant that these Mach 3 capable jets needed a lot of fuel, which obviously involved multiple aerial refuelings. Every time they would have to do that, the pilots would need to slow down substantially, descend and then concentrate on the refueling, a maneuver that was very tiring and time-consuming. Easing those efforts with the help of a faster aerial refueling plane that would be waiting for them a few thousand feet higher up would obviously be a huge help to them. On top of that, the Air Force were also interested in a super big aerial tanker that would be able to not only refuel fighters and the SR-71s, but also large cargo aircraft like the C-5 Galaxy. The project to convert the 747 into a refueling tanker got several names, like the KC-25 or the KC-33, but today they are mostly known as the KC-747s. Like I mentioned before, the aircraft Boeing used to prove this concept was the very first 747 ever built, who was converted into this role as early as in 1972. That aircraft was then fitted with an aerial refueling boom from a KC-135 tanker, and that retrofitting was actually a lot harder to do than it sounds. Firstly, the boom put structural and aerodynamic loads on the aircraft, which the airframe wasn't originally designed for, so that required a lot of strengthening of its internal structure. And on top of that, someone had to also be able to see the boom in order to guide it. That meant that Boeing actually had to cut a window in the rear pressure bulkhead and installed an operator station back there. Obviously, it was Boeing who had also made the smaller KC-135 tanker, so they had a pretty good idea of what they needed to do. But the bigger size of the 747 meant a lot of re-engineering and additional testing, as you might imagine. Eventually, however, Boeing lost the giant wide-body tanker competition altogether. In 1977, the Air Force instead picked the McDonnell Douglas KC-10, which was a variant of the DC-10. The reason was that the DC-10 was a bit smaller and could therefore operate from shorter runways than the early 747s could. But that doesn't mean that no 747 operational tanker was ever built. In this picture, we can see that the same modified 747 prototype that I talked about before is hooked up to another 747, which was being delivered to the Iranian Air Force. That obviously happened before the Iranian Revolution back in 1979, and in fact, Iran received a number of 747s delivered for government and military use during the 70s. Now, the aircraft being refueled in that picture isn't a tanker itself, but Iran did eventually get 4 747s that could both take on and deliver fuel to other aircraft, and at least one of those were reportedly used by Iran in its war against Iraq back in the 1980s. More recently though, countries like Australia have also re-examined the 747 as a possible tanker, but this time based on the newer 747-400 model. But then newer designs based on the Airbus A330 and the Boeing 767 came along, and those plans were again scrapped. But it was not all in vain. Giving the 747 the ability to take on fuel via aerial refueling did eventually become useful. The presidential VC-25 ALSA have this capability, but we already covered that in an earlier episode, so that's not what we're going to focus on next. Over a decade before the VC-25 Alphas were made, the ones you know as Air Force One, Boeing had already started producing 4 other 747s called America's National Emergency Airborne Command Post, or NEACP, more commonly known as NECAP. Their official designation is the E4 Bravo Night Watch, although a lot of people just refer to them as the Doomsday planes. Now, if you see them flying, don't worry, the world is probably not about to end. Actually, if you Google E4 Bravo flight tracker, you'll see that they actually fly quite frequently. So, what are these aircraft and why are they called Doomsday planes then? Well, all 4 of these jets are heavily modified and upgraded Boeing 747-200s, who are, during normal operation, often used to transport the US Secretary of Defense. Their role as flying command post means that the American president might also use them, and if that were to happen, then that aircraft would get the call sign Air Force One. But then the question becomes, obviously, can't the president just use the VC-25s, you know, the plane that we normally refer to as Air Force One, as his flying command posts? Well, as it turns out, the answer, according to the US Air Force, is no, or at least not always. There are 2 things that make the E4 Bravo so special in its role as a flying command post. Firstly, these jets are shielded to withstand an EMP, or electromagnetic pulse, which would normally knock out most communications after a nuclear explosion. Secondly, the E4 Bravos are all about communication. The aircraft interior is arranged with briefing and conference rooms with all the equipment needed to handle communications, well, with everyone, wherever they might be on the planet. But of course, being able to communicate that way means that the E4 Bravo needs quite some antennas, and this is where we get back to that quiz question that I asked you in the beginning of the video. I'm sure that you've already noticed the big bulge that the E4 Bravos have on their backs. Well, that's actually a cover for a satellite antenna. But of course, today a lot of airliners have satellite antennas on their backs for internet access, but the one on the E4 Bravos is obviously much larger. But the question that I asked you was, what is the longest aircraft antenna out there? Clearly, even though the antenna on the back of the E4 Bravo is big, it's not bigger than the antenna of, for example, an AWACS, so we can't be talking about that one. No, it turns out that the E4 Bravo has another antenna, which is even longer than that, actually much longer. And what that antenna is used for is, well, a bit dark. You see, in order to fulfill its role as a doomsday plane, the E4 Bravo needs to be able to communicate with all sites that have the capability to launch nuclear weapons. Now, satellite communication can handle much of that regarding sites above ground, but the E4 Bravo can also communicate with nuclear submarines, even if those submarines are on the other side of the planet and underwater. To do this, the aircraft has a very low frequency transmitter with a power of 20,000 watts. The antenna attached to this transmitter is basically a wire that the E4 Bravos can extend behind it, and incredibly, the length of this wire when it's fully extended is a full 5 miles, or about 8 kilometers long. This gruesome party trick is something that is unique to the E4 Bravos, and even the new Air Force One aircraft, the VC-25 Bravos, won't be equipped with this, at least as far as we know. And that's the reason that the normal Air Force One can't serve this somber role. This, by the way, is also the reason why the Air Force wants to replace the aging E4 Bravo fleet over the next few years with some type of new aircraft. For a while, there were plans to replace them, the AWACS aircraft and other intelligence-gathering jets, with something based on the 767. But the Air Force really wants the new E4 Bravo replacements to also have 4 engines, so we will have to wait and see what they come up with there. In any case, this is the reason why whenever the US president goes on a trip abroad, one doomsday E-4 Bravo plane will always follow him, staying parked at an airport no more than 1 hour or so away, in case something really, really bad would happen. So now you know that, but I'm not finished yet. Finally, there is another, more recent and seriously strange-looking 747 who actually also was supposed to play a role in the potential end of the world, but this plane was designed to try and stop it. The name of this project was the Yankee Alpha Lima 1 Alpha, a giant airborne laser. The purpose of this aircraft, and also of some earlier projects based on the KC-135 tanker, was to use a powerful laser to destroy incoming intercontinental ballistic missiles, or ICBMs, while they were still climbing out through the atmosphere after their launch. To do this, the YAL-1 Alpha had a megawatt-class chemical oxygen iodine laser, or coil, mounted on its nose. It was also equipped with a set of less powerful lasers to be used for the tracking of those ICBMs. This project was constructed from a brand new Boeing 747-400F freighter, meaning that that giant laser gimbal could be mounted on its forward cargo door. It also had aerial refueling capability, and it first flew as late as in 2002. A number of tests were conducted with this aircraft, including actual shootdowns of simulated ballistic missiles. The idea was that if this would actually work properly, a fleet of these aircraft would be created could patrol the skies in certain parts of the world looking for the launch of ballistic missiles. But sadly, that's not what ultimately happened. It turned out that even a megawatt-class laser wasn't powerful enough to do the job it was designed for. Even though this aircraft did destroy some test missiles, it had to be quite close to them in order for it to work properly. Research showed that in order to be able to do what the Air Force wanted, the laser would need to be 20 to 30 times more powerful than the one fitted to the test aircraft. The Air Force continued using the YAL-1 Alpha Jumbo for a few more years, mostly for research purposes, but then the aircraft was put in storage and finally scrapped. And I personally think that's such a shame. I think there's something both terrifying and beautiful in the thought of a laser-shooting queen of the sky. But with the production of the 747 now over, it's not clear if we will ever see any other military or research jumbos being created. But you never really know. Airbus is using its A380 for research on new engines, for example, so it's perfectly plausible that someone, somewhere, will find a need for something as big as a 747 for some new strange project. But hopefully not to try and destroy the world. Now, check out this playlist if you want to see more wonderful rolls of the 747, or check out this video up here. Also, consider supporting the channel by sending a super thanks, buying some merch, or becoming a patron. It really helps. Have an absolutely fantastic day, and I'll see you next time. Bye-bye.